completed his PhD under Romain Wels and Etienne Torre at INRIA. And he's going to be talking about slow, fast, and long-time behavior analysis of a neural network with stochastic STDP.
Exactly. Do you hear me well?
Yes.
Okay, so let's go. So hello, everybody. Thank you. I would like to thank the organizers for enabling me to talk about my joint work with Etienne Torre and Romain Wels. So on slow, fast, and long-time behavior of a neural network with a stochastic STDP. So it's a bit related with the work of Gaëtan. And I will first give the motivation of of our work, and then give the presentation of our new model, and go on to speak about our mathematical results and illustrate them before giving perspectives. So our work, in our work, we wanted to use mathematical modeling and mathematical analysis in order to get more insight in the interaction between the dynamics of the synapses and the dynamics of neurons. So there exists a few mathematical results, as Gaëtan said, on plastic neural networks. The main reason is that because it's quite difficult, because it involves the coupling between the dynamics of the neurons and the dynamics of the synapses. And one way to simplify such model is to use the timescale difference between the dynamics of the synapse and those of neurons. And it was first done by Kemp and his collaborators and his colleagues. And it follows a lot of numerical analysis. And since a few years, there are more and more mathematical results on the plastic neural networks. And for instance, I just gave 3 of them. So the work of Galvez and his collaborators on short-term plasticity and using mean field methods. Torres and Salor studied neurons that are modeled by time-elapse models, and they study the long-time behavior of this neuron interacting with synaptic weights that are plastic. And finally there is the great work of Robert and Gaëtan that he explained us just before. So in that context, we proposed a new model with a stochastic plasticity and discrete synaptic weights. This model we propose it because to have a biologically realistic model, and we wanted it to be mathematically tractable, and also we wanted a model that we can simulate with a large number of neurons. And we then studied it using biological assumptions, mainly this timescale difference, and this enabled us to do slow fast analysis, and we then obtained a reduced model that we then studied its long time behavior. So I will first present briefly, because it has been presented before, the STDP, so the spike timing dependent plasticity mechanism. So if we consider 2 excitatory neurons, we want to know how the weight Wji will evolve depending on the spiking times of the neuron I and J. So what has been observed is that when the presynaptic neuron I spikes will cause repeatedly the spikes of the neuron J, we'll observe an increase, so long-term potentiation of the weight Wji. And in the other way, we'll observe a depression of, so a decrease of this weight. And this has been studied experimentally, and it has been shown that there is an interesting dependence in between the spike timing, so this delta t, and the change of the synaptic weights. Well, another thing which is interesting is that we need a lot of spike pairs before observing a significant synaptic change, so synaptic weight change. So we can model this phenomenon by two ways. So whether we consider infinitesimal increments of synaptic weights each time we have a spike pair, so yeah, it spikes, or we can, so this leads after a large number of spike pairs, this will lead to a macroscopic change. This is done by Kempter and the following studies. And another way is to consider macroscopic change each time we have such a spike pair, but this jump will have a small probability to happen. So this is the way we model the plasticity, and this leads to stochastic plasticity and to discrete synaptic weights. And this seems to be more biologically realistic, because synaptic weights should be mainly discrete because of the number of chemical and molecules that are responsible for this plasticity, so for the synapses. So this has been shown by O'Connor. So now I will present you our new model. So we use the stochastic Wilson-Cohen model for the neurons, in which we added the given STDPs that I will describe. So we consider a network of n interacting neurons that are described by their potentials that are binary and that will be noted by VT. And these neurons are connected by the synaptic weight matrix that will denote by WT. So this matrix is it takes integer values. So we will consider only excitatory neurons, but some of our results hold also if we consider inhibitory neurons. I will tell you which results still hold. So I will present now the dynamics of the weights. So our weight will change as soon as one neuron spikes. All its incoming and outgoing weights have the possibility to change. So first, all the incoming weights will have the possibility to increase with the probability P+, which will depend on the last time, the last spike of the neuron, so in that case, the neuron J. So we see that this variable S will correspond to the delta T that we presented in the experiment of B and Poo. And so in the other way, the outgoing weights will have a probability to decrease, which still depend on these times in the last spikes. The function P plus and P minus, P plus and P minus are taken to approximate the results of BNP, or you can also take any functions, because we know that there are a lot of different STDP curves. So in this example, I show you with the approximation of the experimental the experiment of BNP. So now we have to add this ST in our variable, and also we need to describe the moment that we consider to be a spike, and this moment will be the jump of the potential from 0 to 1. So I show you here in the graph that when the neuron 2 jump from 0 to 1, we will just reset the corresponding S to 0, and etc. So we add in the dynamics that when the neuron I is spike, the corresponding S will be reset to 0. So now we have to describe the dynamics of the potential, and these dynamics will depend on so the spiking rate, so the jumping rate from 0 to 1 is a function of the synaptic current entering into the neuron I, and the jumping rate from 1 to 0 is constant because we want to model the time of a spike, which is quite constant in the biology. And one last thing is which is important is that we consider that the spiking rate is bounded, and yeah, also the alpha curve is can be considered to be a sigmoid in general. So now I will just give you a last example to be sure that the model is clear. So if we consider a 3-neuron network, we can just now show how it can evolve when the neuron, for instance, the neuron 1 spikes. So we see that just before the spike of the neuron 1, the network was in that state. And when the neuron 1 spikes, so you will have the jump from 0 to 1 to the neuron 1, and the jump of the corresponding S so the reset to 0, and you can have a change of the weight. So the outgoing weight can decrease. So for instance, this one has decreased, this one did not decrease, and the incoming weight can increase. So now we have presented this model. We want to study it mathematically, and so we cannot do it with such a model because it's quite complicated with this dynamic on the synapse and this dynamic of the neuron on the neurons. So we will make the assumption that the plasticity is really slow compared to the dynamics of the neurons. So we will introduce a parameter epsilon, a small parameter, that will be used mainly in the definition of the function p plus and p minus. And we will assume that now the probability is epsilon p plus and epsilon p minus, the probability of jump of the weights. So we see that now we will be interested in the dynamics when epsilon tends to 0. So we see that this process, this adding of epsilon will make the weight be fixed in that limit. So the first question we can ask is, does the process Vs has an equilibrium for when the weight matrix is fixed? And then we can study the dynamics of the weights on the fast scale, and then we will obtain a non-trivial dynamics of this of the weight on this time scale. So first we need to spare the state space of our process. So we'll consider that E1 is the state space of Vs, and E2 is the state space of the weights. So the first result we have is to show that when W is fixed, so the synaptic weight matrix is fixed, we can show the convergence of the process Vs to a given invariant measure that will depend on W, and this occurs exponentially. This result is shown using the criterion, the doubling criterion. And after that, we then study the the process W on the faster time scale T over epsilon. And we show that this process will converge to a process W bar, which is a pure jump process that is defined by its jumping rate between W with that can be jumps that can make the weight jump from W to W plus EIJ or minus EIJ, where EIJ are is the canonical basis of the square matrix, the n square matrices. So what is important is that these rates Rij will depend deeply on the invariant measure PW. And so now we have these dynamics. We wondered how we could study the long time behavior of this limit process W bar. And we can, to do so, we can use the so-called Forster theorem. And with this theorem, given the Lyapunov function, we found that we can find condition on the jumping rates of the W bar, such that the process W bar will converge to a unique invariant measure. We have the same results for divergence, using the fact that instead of this condition, we will have this left term that will be lower bounded by alpha big M by capital M n square. Just to come back to the assumption, the first one is just to be sure that our process is irreducible and aperiodic. So this is a nice result, but we still need to compute this Rij and plus and minus to be able to use it. So to do so, we use the Laplace transform of PW that appears naturally in if we write P plus as exponential, if we consider P plus to be exponential. So this is where the Laplace transform appears. And we can also have a similar result. So use this Laplace transform in more general cases. So if you can write P plus and P minus as a Laplace transform of other functions. So now with this results, we are able to compute the Laplace transform of PW in the case of only two neurons, and we can in that case. So I didn't put all the parameters, but I took general parameters, and we can see that we have the convergence that we have proved. So this is for epsilon equal to 0.01, and for 10,000 trajectory, we obtained that the distribution at after 3 seconds is quite close between the particle is the initial system and the Laplace is the W bar trajectories. And we can also see that, which is classical, that when NMC increase, we have the distance. So this is the L1 distance between the distribution of the initial system and the limit system, and we see that this distance decreases. So this is our theorem proves this. And another thing that we did not study yet is the speed of convergence, and we see that. So this graph shows a bit like how it will converge when epsilon tends to 0. So how the distance between the two distributions will converge. So here it's for 5,000 trajectories of our process. So now I will illustrate the fact that we can, thanks to these computations, we can find parameters for which we have either convergence or divergence of our weights. So we'll take the spiking rate function to be sigmoid like that. We'll consider the parameter, these parameters. And we observe that so with these parameters, when we take A plus to be equal to 0.2, we'll have our weights which will converge, so in distribution. And if we take A plus to be equal to 0.3, so if we just change a bit A plus, we'll observe divergence. So this can be obtained using our mathematical results. And a natural question when we have such results, we can wonder if the parameters involving convergence of weights in a two-neuron network would also imply the convergence in a larger network. So we did this computation, and with 100 neurons, we observed that computing the average value of synaptic weights over time, we have convergence of our weight until a larger value of A plus, so until 0.5, and we have divergence approximately beginning at 0.6. So this may, so after this computation, it's interesting because if we can only find condition on the two-neuron network, it costs really less than for bigger networks. So this is one of our perspective, is to show that the analysis of on two neurons is sufficient for the weight convergence analysis of more neurons. Also, what would be an interesting thing is to control the distance between the initial and the limit systems. So here we have our theorem tells us that when epsilon goes to 0, we have the convergence, and we studied the long-time behavior on the limit model. So if we want to come back to the initial model, we have to control this distance between the limit model and the initial model using this, so yeah, in function of epsilon. So we could do, so we are trying to do a central limit theorem on our results to obtain such results. And then we would like to, there are many ways to extend our results and our models. So first we could put the time since the last spike S in the spiking rate, that which maybe, for instance, Gaëtan did this. Also, we could have a continuous membrane potential and try to find similar results, getting rid of the bounds on the spiking rate. And finally, what would be interesting is to investigate the memory capacity of this model. That's a thing that is commonly done in a model of a neural network with plasticity. So to do so, we have to define a learning protocol, and then we will have to define and study a learning to how the network learn a signal. So we could use the signal theory to do so. And finally, what is really interesting is to combine the mean field analysis and the slow fast analysis, because so we did a mean field analysis on this model And in order to have the simplest possible model, we could hope that we can combine these two studies. So thank you for your attention, and if you have any questions, thank you.
Okay, thank you, Pascal, for this very interesting talk. We have time for questions. One of them is on your last point, the mean field analysis you mentioned. Is this numerical, or is this mathematical that you did?
So it's mathematical analysis. So we did. So we have So we had to assume the convergence of the empirical measure. And since we assumed this convergence, we were able to find the limit model.
Okay.
But yeah, so there is still this convergence that we have to prove to be
okay,
to be complete. And yeah, we did some simulation to test this limit model, and it seems to work well.
Okay. And so if I followed you correctly, your membrane potential can take two values. Is that, am I correct?
Yeah. It's
right.
very,
So do you expect difficulties in the adventure of going to continuous membrane potentials?
Yeah, the main difficulty would be to control this membrane potential to prevent it from going to infinity. But if you consider a model such as the one of de Massy and Fournier, in which you have a reset when you have a spike, you can expect to have the same results without a lot of effort, I think.
Thank you. I see a question by Priscilla Greenwood. She's asking convergence rate for many neurons, question mark.
Yes, Pascal, I liked your talk very much. And starting with 3 neurons, that's great. And then you went to 100 bravely, 100 immediately. And my question, and you still had convergence. And my question is, did you compare the rates of convergence? When you have so many neurons, does this slow down the system by some amount, or is it still converging quite nicely?
Yeah. So yeah, we can see. I didn't study it in detail, but we can see here that the average is still quite high after 300 seconds, and in the previous one, so yeah, I didn't. So in the previous one, we see that the weight, which is the bigger, stay far from zero until let's say around 10,000 seconds. So yeah, I didn't go far enough to compare it. But yeah, because yeah, when you take so much neurons, and as I did computation, I take in memory all the values through time, so it's quite heavy with 100 neurons. That's why I didn't go further. So.
Okay.
Thank you.
Perhaps one last question by Sven Gödicke. In the limit, you consider the rates at which weight changes occur go to 0, but the amplitudes are finite, question mark.
Sorry, what? Can you repeat the question? Sorry.
Yeah,
Sven,
I go online maybe.
Yes.
Yeah.
Online.
No, I was. Yeah, thank you very much. Very interesting. So I was just wondering. So how can I just like intuitively imagine the dynamics in the limit? So if I understand correctly, So
I
because
think I understood.
yeah, so that the jumps of the weights are still finite, but they occur more and more rarely. Is this correct? Or
Yeah, that's it. Yeah, usually you have the size of the jump will decrease with epsilon. So
yeah.
so you will have this fact that you need a lot of spike pair, and as you are looking on the fast time scale, you have a lot of spike pairs. So you observe on average something which is finite. And in our case, it's thanks to this probability which is slower and slower.
Yeah. So
smaller and smaller.
So that.
Sorry. So yeah. So if you look at on average, you will have a lot of spike pair, and you will see that there is one change of weight for all these spike pairs.
Yeah.
I don't know if it's answers the question.
Yeah. Thank you very much. So I was just wondering how would you do this, and if you want to like simultaneously let the network go, or not simultaneously, but also consider like a mean field limit for the network size, then it would be difficult to keep this rarely or
the mean field limit is we will consider we'll add in the spiking rate we will add 1/n in the here.
Okay.
So yeah.
Okay.
And
sorry to interrupt you guys. You can continue the conversation offline, but thank you again, Pascal, for this very interesting talk.